One of the common examples often used to talk about recursion is the idea of a fractal. So a fractal is a geometric shape that is related to recursion because it's repeated on smaller and smaller levels. It's the same shape repeated again and again and again, smaller and smaller. You can easily do an Google image search and you can see all different examples of fractals, and you can see that again the idea here is that a shape is repeated over and over and over at smaller levels all the way down. Fractals appear in a lot of places, but one place that they appear in is just in nature. So you can also kind of look for examples of that. You can see them in, shells and flowers, and here's one in peacock feathers and trees. So all sorts of different places that fractals appear in the natural world. And hopefully you can kind of see again how this is related to recursion because it's a shape made repeated smaller, repeated smaller, repeated smaller. So to just kind of give you an example of a graphical example of recursion, we're going to take a look at a program called Recursive Squares. So what I'm going to do is I'm first going to show you what the outcome is going to look like, and then we'll take a look at the code. So this is the idea of what we want to draw. So you can see that this is a square, and then on each corner of the square is another square, and on each corner of that square is another square, and so on and so forth until we reach a minimum size. Now let me pick a bigger minimum size so you can see this a little better. So this would be kind of one layer. So we draw one square, and then we would say at each corner, draw another square. Okay. Now, if we continue on, we could say, okay, now we have enough space. We draw one square. At each corner, we draw a square. And then for each of those squares, at each corner, we draw a square. So the idea is we kind of, again, reduce the size and repeat that shape again and again and again until, in our example here, I've just made a minimum size so that we can at least see the smallest square. The reason I like this example is because it does sort of make you think about this kind of thing in the real world, again, with like the shapes and nature that we just took a look at, but it also gives you a sense of kind of the exploding efficiency or inefficiencies of recursion, because you can see that when you start out, you have just a single square. And then as you move along in recursion, you have, okay, so drawing the smaller squares on a single square requires you to draw 4 of them. But now we need to draw 4 on each of those. So now you're drawing 16 squares. And if you were to keep going, I'm not sure I can make this big enough, you would draw many more than that. So you can see how there's this exponential nature to how recursion can grow. So that's why it's really important to think about that. And anytime you're going to be dealing with, a large data set or something like that, recursion might not work because of that growth. So let's take a look at the code, and I'm going to set this back to, I think I had it at 20. Yeah, so that looks good. Let's set that back to that, and we'll take a look at the code. So I've set this up in JavaFX. So I just have some constants about the shrink factor, the initial size of my window, and then the smallest I want my square to be. And the idea here is that I'm going to create smaller and smaller squares and then add them to a group, which is part of our overall scene graph, so that more and more smaller squares can be seen. So I just kind of set up the initial window. Now I have this line in here that listens to the changing of the window size. That is just for the purposes of kind of being able to see additional layers of recursion being added on. Don't worry too much about the code for that. And if you want to kind of disable that so you can not be distracted by that, you can just set the window to not be resizable. And then you can kind of just look at it for one size. But I just have that in there about resizing the window because I think it can be kind of helpful at understanding, how recursion works as you kind of go split off into more and more directions. So what I do here is I have a method called create display. And what create display does is it just clears out any square, any group, any children that are already in the square group. And this is just for the purposes of if we are going to redraw every time we resize the window. That's why I do that, so that we can create new rectangles each time with based on the changing size of the window. If you weren't going to change the size of the window, you would not need to do that. And then I create the size of the initial square, so that's the square in the center, and the initial X and Y placement using these values. Now these I've just figured out through trial and error, and these are placements and sizes that I think look good. You can play around with this code and kind of change those numbers and kind of see how that makes your design look. Okay. And then what I've done is I've called a method called create square. So the idea of the recursion here is, this is a really hard problem. I don't know how to solve this, but I could draw a single square. If I draw one square, that's my small part of the problem I can solve now. Then I could ask somebody else to draw the additional 4 squares. That's the part of the problem I'm going to solve later. So the idea is, again, create square draws just a single square and then calls itself to draw those 4 smaller squares. So we're essentially going to have 4 recursive calls. So to create that square, I need to tell the method where the square should go, so the x and y, and I need to tell it how big it should be. Now, I also need a base case. So in here, I've just said, I actually just have a recursive case and my else is an implicit base case. I've just said, as long as the size of the square I'm trying to create is greater than or equal to the minimum, I'm going to go ahead and I'm going to, run the code to create the square. And once I reach that minimum, I'll jump down to the else and be done. So I actually create the rectangle just with that x and y and size, and then I set it to be pink and I add it to the squares group. Now I create these 4 variables, left and right x and upper and lower y, just to kind of make the code a little clearer. You wouldn't have to do this. You wouldn't need these local variables. You could do it without it, but I think it kind of helps understand what's going on. So then what I do is I say, okay, this is the small part I'm solving now, right? Adding 1 square to the group, to the scene graph, I'll say, to the group. Okay, and then this is the part to solve later. Okay, so when I'm drawing those squares, I'm going to reduce the size of my square by whatever factor I've specified as a constant. And again, you can kind of play around with these constants to see what the display looks like when you change them. And then I'm just going to have these 4 recursive calls. So in each recursive call, I'm going to create a new square and I'm going to give new x and y locations and the new size, this reduced size. So the new x, so let's look first just at the upper left. The new x location of the upper left is going to be whatever the left x of my current square is minus some shift, right? I want to move it over a little bit. So the shift is defined as the size divided by the shrink factor divided by 2. That extra divided by 2 is because you want your new square to be centered on that corner. So you're not putting the new left corner of the smaller square on the old left corner. You're putting the center of the square on the old left corner, if that makes sense. So that's my shift. So for the square I'm going to draw at my upper left, the new x is going to be whatever my current left x is minus that shift. My new y is going to be whatever that current upper y is minus that shift, and then it's going to be the new size. For the square I want to draw at the upper right, it's going to be the x value is going to be the right x minus that shift, and the upper y minus that shift. The square at the lower left is going to be the left x minus the shift and the lower y minus the shift, and the square at the lower right will be the right x minus the shift and the lower y minus the shift. Okay. And that's pretty much all there is to the code. Now, what's kind of neat also about this is if you comment out some of these recursive calls and just look at one at a time, you can kind of see exactly what's happening. So this is the draw the square at the upper left. And here you can see that, whoops, if I can keep it on the screen. Oh, I made it too small. So you can really see what's going on here, that on this first square, I drew a square and then I recursively asked to draw another square on the upper left. Then I took that square and I recursively asked to draw a square on its upper left. Then I took that square and recursively asked to draw a square on its upper left. I took that square and recursively asked to draw a square on its upper left. But at that point, the size has been reduced such that it's smaller than the minimum, so I'm done. And you can kind of see that for each of the different corners. So this was our upper right. Lower left. And lower right. Okay. So hopefully this kind of gives you sort of a visual idea to think about recursion, and sometimes this one's kind of cool. You can do two at once, right? So sometimes that can be helpful in sort of thinking about it and how it looks. So I encourage you to play around with this, play around with what different shrink factors look like, different starting sizes. I also encourage you could think about how would you write this for a different shape? So how would you write this for a triangle with a smaller triangle at each corner, right? Or how would you write it for a hexagon? Okay, or something like that. The idea is going to be the same. The main difference where you'll have to do the work part is to figure out those new coordinates. What are we shifting by, and what are those new x and y values? So that would be kind of the hard part of the problem. The recursive part in this case is actually pretty straightforward. And again, the idea is solve a small part now, recursively ask that method to solve the rest of the problem later, and know when to stop.